So I guess let's get started. Can everybody see my screen? No.
Yep. Yep.
Great. Here we go. Okay, so I'm going to talk about causality, and I'm going to also talk about how that relates to artificial intelligence and machine learning. My name is Scott Mueller. I'm studying, working towards a PhD in computer science at UCLA. And I'm very fortunate to be working with Judea Pearl, who's widely considered now to be the father of causality. Causality has actually been around a very, very long time, but Judea Pearl has contributed some really substantial tools and knowledge to the world of causality. And for that, because it relates to artificial intelligence, he won the ACM Turing Award. The ACM Turing Award, if you're not familiar, is similar to the Nobel Prize for computer science. We don't have a Nobel Prize in computer science, so this is what we have, which is equivalent in prestige. So I'm going to talk about, I think there's 6 topics: causes and effects, determinism, probability, experimentation, counterfactuals, that's the big one, and then how it all comes back and relates to artificial intelligence and how machine learning in today's AI is going to be progressing moving forward with causality at its core. And by the way, I'd love for this to be interactive. So if anybody has any questions or just wants to interject with a thought, please do so. And I'll ask some questions along the way to try and make this a little more fun. So what are X and Y? We have a little miniature graph here with 2 nodes, an X pointing to a Y. And we can think of these as a cause and effect. X causes Y. Might be medicine for X, and Y would be whether you're cured or not. So if you take the medicine, hopefully that makes you cured. That is the cause of you being cured. We can similarly think of them as study for the X node or X variable, and Y, the outcome is that you ace your test. Here's another one that seems pretty clear. You flip a light switch, that should cause the lights to turn on, or a light to turn on. So the next question is Y perfectly predictable? If we flip the light switch, will the light always turn on 100% of the time? Not always, of course. Maybe this will be the first question that I ask everybody. What could have happened? Why would that not work?
Could have had a power outage, perhaps.
Yes, power outage. The bulb could be out. The light switch itself could be defective. It could be a wiring issue. A number of situations could occur. But typically, when we're in our house and we go into a room and we hit the light switch, we expect that to turn on. So we draw this graph and we're pretty comfortable with that graph. Even light switches occasionally fail. So this isn't a perfect graph then. X doesn't always cause Y. The medicine that we take doesn't always cure us. We have a headache, even though there's a super powerful, amazing new headache medicine that has maybe always worked for us in the past. This time it doesn't. We have this test coming up. We think we're pretty smart. We study like crazy for it, but we don't get the performance that we wanted from that test. So it's not perfect. So maybe we just need to add some more nodes to the graph. Maybe Y doesn't just have X as a cause. Maybe there's another cause for Y too. So X could be the light switch and Z could be the state of the bulb. Maybe Z is the state of a number of things: the bulb, the wiring, the light switch itself, the electricity coming in. And so, okay, we just need to keep adding nodes and then we will get perfect prediction. Here's another graph that we could think of where Z not only is a cause of Y, but is actually the cause of X as well. We'll see some examples of that, but you might think of medicine and cured. You've got a headache. Well, the headache itself caused you to take the medicine, and the headache will affect whether you're cured. Whether you're cured depends on whether you have a headache and you took the medicine. Before I talk more along those lines, I just want to mention determinism. I don't know how many of you recognize this photo. This is Spinoza, a very famous philosopher. He was a Jewish Dutch philosopher, 23 years old. He was expelled and shunned by Jewish society because he came up with this notion that causal knowledge determines everything. That's where we get the word determinism from. So if we just knew enough of the nodes in our causal graph, we could tell you absolutely everything. Oh, I've got some chat stuff. Let me make sure I'm not missing anything.
I think he expected to see a picture of the philosopher you're referring to.
I think you might be a slide behind.
Oh, okay. So are you all, is everybody all set now? Can everybody see this slide?
We can see the causes and effects slide.
Oh, you can't see the determinism slide?
No.
Huh, that's weird.
Is it loading on your end?
I'm gonna stop the sharing and I'm gonna share it again. Can everybody see the determinism slide now? No?
Now it says Scott Mueller has started screen sharing. It's just a black screen.
Wonder what's going on. I've never had this problem with Zoom before. I stopped sharing. I'm going to share it one more time. And if this doesn't work, I will.
I have the slides, so I could share them if they don't work for you, Mr. Mueller.
Yeah, I was
Okay.
just about to propose that. That's a good idea.
Let me try one more thing and then I'll take you up on your offer, Damien, because these slides, I have to press it. Well, if you don't mind pressing the space bar over and over again while it goes from line to line. And maybe, can everybody see my Chrome browser now?
Oh, there it is. We can see it.
Okay. Huh. Strange. Somebody mentioned in Human Chalk, mentioned Ken Dad. Yeah, I think some of you know my son, Ken Mueller. I'm his father. So Spinoza, he came up with this idea that causal knowledge determines everything. So we can imagine that in our causal graph, which represents maybe a person and the outcome of some treatment on that person, we have all the nodes for the person, 10 quadrillion of them, and they encapsulate every single thing we can possibly know about a person, and where every single atom is accounted for. Then we could know whether you would be in fact definitively cured from the medicine, maybe what your next thought would be if we had knowledge of how everything was happening in your brain at that moment. This is also known as Laplace's demon. Some of you may know from maybe a math or philosophy class, Pierre Laplace. I won't read this whole thing, but he basically is saying the same thing. I'll read the first sentence. We may regard the present state of the universe as the effect of its past and the cause of its future. But it turns out that there are a few problems with that notion. And I'll talk about probability and we'll circle back to that. But probabilities actually get pretty advanced, and hopefully some of you will study this in high school and college and beyond. But the basic idea is just, you count the number of desired outcomes and you divide it by the number of total outcomes. So based on that, you can see that probabilities are always a number between 0 and 1. 0 means that the event is impossible. The probability of that happening is, when you say the probability of something happening is 0, that cannot occur. If the probability of something happening is 1, that means it is a complete certainty. So I have an example here, rolling a dice. Apparently, I read that die is no longer refers to one single dice. You say dice even if you're just talking about one. So if you just roll one of these cubes, what is the probability that you get a 5? Can anybody answer that?
If you roll one dice, we have 1/6 chance of there.
Right. So one desired outcome divided by 6 total outcomes. So it's 1/6, and the probability would be 0.16, and the bar didn't quite render right, but it's 16666. So the probability of rolling 2 dice for a 5, that means one dice could be a 1 and one dice could be a 4, or a 2 and a 3. This is 4 desired outcomes, a 1 and a 4, a 2 and a 3, a 3 and a 2, 4 and 1 out of 36 total outcomes, and you get 0.11111. If you want to roll 2 dice for a 7 or 11, here's all the possibilities for a 7, and here are the 2 possibilities that you could have for an 11. That's 8 outcomes out of 36. That's 2/9 chance. Turns out probabilities are pretty important in just about everything we do. At the quantum level, I think the consensus now is everything is probabilistic. And the next slide talks about probabilistic things, but we at the bottom level, or the bottom level as we know right now, things happen at chance, but according to what's called a probability distribution. So it's very, very, very unlikely that things will not happen as you expect them to. And so the book, one book that my professor Judea Pearl wrote, Causal Inference and Statistics Primer, describes probability as a way to express our beliefs and uncertainty about the world. I put this image here as the probabilistic nature underpinning everything. This is an imaginary image I just found off the internet of what things might look like, but it's not relevant. So probabilities overcome these limitations in our knowledge. Before I talked about how maybe we just need more nodes in our graph, in our causal graph, to really understand what's going on, to really be able to predict whether medicine will in fact cure you, or whether studying for a test will in fact get you a particular score, or whatever it is you're trying to infer or understand. Well, we can't know where every single atom is. Actually, there's some fundamental theories in physics that prevent us from knowing the exact location and speed and all that of particles. But we can assign probabilities to these things with a very high degree of accuracy. So, ultimately, we can never add enough nodes. And much of science is discovering 2 things: effects of causes. So, you give somebody the particular medicine or food or some kind of treatment, what is going to happen? It's probability of being cured from a medicine, probability of being acing. I wrote that wrong. Of acing a test from studying, and it can get a little more interesting. So it's not just acing a test from studying, but given that you have 175 IQ, or compare that with studying a certain amount for a particular test, given that you have 170 IQ or 165 IQ, and you can see the differences. Or now again, we have this probability of light turning on from flipping a switch, but we don't have the exact knowledge of what's going on, but we have probabilities of what's going on behind the scenes. The probability of a defective bulb we know is 1% or 0.01. The probability of a defective switch is this. So you put them all together mathematically, and you can get the probability of light turning on from flipping a switch. The other thing that we try to do in science is, one of the other things is understand the causes from the effects. So we see the outcome, we want to know what caused it. And this is a pretty big part of science. So what is the, and here using our same examples, our same toy examples, what is the probability that we had flipped that switch when we see the light? So that's probably a very high probability, because it's unlikely that we see a light turn on and it just spontaneously happened. It could, again, from a defective switch, probably not from a defective bulb, because you need electricity there too. Or, you know, this might be a question of, you see the light on, it didn't turn on, it's already on. So, and then here's a more astronomical one. Probability of a planet passing by when a star's light dims. That's one way we tell about planets. So we want to be able to understand these probabilities and effects of causes and causes of effects. One way we do that is through experimentation. And historically, experimentation, this is how a lot of our previous scientific knowledge came to be. And this is instinctual for us. You know, when we look at something, we automatically assume causes. We think about the causes at the very least. There are many lessons throughout history where we thought we understood the causes. We thought the Earth was the center of the universe, and everything spun around the Earth, all the stars and the sun and the planets. And in fact, Ptolemy had really elegant and nice ways to mathematical formulas to show that. But we could be wildly wrong, and we have been many, many times. So how can we be sure? How can we even start to imagine what the causes might be? And this is where experimentation comes in. And even as kids, we instinctually engage in experimentation through playful manipulation. You know, we stack blocks on top of one another and we see what happens. We pull out the bottom one, we see them all fall. And this is how we grow up and manipulate our environment to understand what's really going on. And so we can come up with hypotheses and then test them. Does the medicine work? Well, we can, you know, we think that this herb or these set of chemicals put together, when ingested, will get rid of headaches or cure cancer or cure COVID. And so we come up with an experimental procedure. And one very, very popular way that is proven effective are randomized controlled trials, RCTs. So you separate people into control and treatment groups. The treatment group gets the treatment. The control specifically does not. Whereas, you know, if they were, maybe you're testing Tylenol's effects on something. Well, you know, if somebody might be taking Tylenol, you know, just because they felt like taking it, not part of the study, you know, you expressly forbid them if they're going to be in the control group. And then you look at the difference in the outcomes. So you calculate or count the proportion cured when you gave them or forced them to take the medicine, and you subtract from that the proportion that were cured when you hadn't given them the medicine. And that seems like a really effective way to understand how beneficial this medicine was. So, and I hear these are some interesting questions. So the question, so there are three possibilities here three that I wrote here. It was beneficial, the medicine, if this calculation above, this subtraction, is positive, which means that the proportion cured when given the medicine was greater than the proportion cured that did not have the medicine. If that's the case, it would seem intuitively reasonable that this medicine benefited people, that it benefits people. It's good. It's a positive thing to do, to take when you have that illness. And of course, if it's negative, then it was harmful. So my question is, I'm curious if anybody knows this. Was this medicine just useless, totally ineffective? Was it the same thing as not taking any medicine at all?
I would say no. In the real world, perhaps the people or the people you tested the medicine with, their body, I guess, rejected it. Perhaps.
Is that you, John, talking?
Yeah, it is.
I saw your lips move, but I couldn't. I heard no in the real world, and then I didn't hear anything else.
Oh, can you hear me now?
Yes, I can.
Yeah, perhaps, the individuals you tested, their body perhaps rejected it, and it just caused, nothing happened, right? It might be specific to that person. So I think that would be more likely if you tested a large amount of people.
Let's assume that it's a large enough proportion, a large enough number of people where those individual effects get averaged out.
I would agree that would mean that it has no effect then in that case.
Mostly. Right, and Dennis Chunikin mentions on chat, maybe slightly worse because of placebo effect. Now, let's say it's double blind. Nobody knows whether they have the placebo or the medicine or the actual medicine. And so what could be happening here is that that maybe half the people that got the medicine, they were cured because of the medicine. They had an illness. Let's say let's take it to the extreme. Let's say they had a deadly cancer, and this cancer, it is really, really bad. But for 50% of the people that took this medicine, it absolutely cured them. If they had not taken that medicine, they would have died. But they took this medicine, and now they are alive. So this medicine was a miracle cure for them. And then the question you might be asking is, well, if that's true, in this when they were given the medicine, that 50% of the people were cured, well, wouldn't we see that reflected in this proportion cured without the medicine? Wouldn't we see that those equivalent 50% of the people died? And the answer is yes, but that could have been offset, because the proportion in the treatment group, the other 50% of people, they died because of this medicine. Had they not taken the medicine, they would have lived. They would have been cured automatically just from their natural body's defenses. But this medicine had a toxic effect too. Sort of like chemotherapy or radiation therapy, they can be toxic to your body as well. And for those people, this medicine killed them. And you see that in the proportion that were cured without the medicine, the equivalent 50% of people that were killed now survived. And so, we see that actually this medicine had a tremendous effect on people, and absolutely cured some people and killed other people. There's something really special about this medicine. And we just need to figure out what's the difference in these people, what component of the medicine actually cured these people, and we have this miracle drug on our hands that can save so many lives. But this wouldn't actually be passed by the FDA if all you showed them was there were a zero average effect when we gave the treatment group the medicine and the control group. We would say, oh, there's no difference. So are there limitations to what experiments can tell us? Well, that's one limitation. And there are, of course, many other limitations too. Can anybody think of another limitation limitations with experiments as well in general? I mean, here we have an example where It can't dig into the probabilities as we would like. But what else can't we know from experiments? Claire says causes. Yeah, so that's an interesting causal. We can only know correlations. Yes, that is true. There are ways that we can figure out the causes, and we can eliminate. There's just a little aside. I'm sure most of you have heard there's no correlation without causation. It turns out that actually whenever you see a correlation, a true correlation, not a spurious correlation like coincidence. Coincidences go away when you have enough data. So let's assume that this is not a coincidental situation. Whenever you have a correlation, it is a causal situation. Which you know, you hear the no causation, no correlation, or correlation is not causation. But I think that's not a good way to look at it, because it always involves causation. It's just that you don't know the direction of causation. And so so you can see with experiments correlations, but you may not know what the direction of the causation is there. Well, you can run other experiments to figure out the causations there sometimes, but it's true that sometimes you cannot. My math teacher tricked me, right? So ice cream sales lead to house burglaries, Kai. So some students here are previous students of mine, Kai and Claire being two of them. So another limitation is there are ethics involved. You can't force somebody to smoke for 30 years to see the effects of smoking. You can't, other experiments are feasibility issues. Are 2,000 light years away to see how it dims the star. So experiments are pretty limited in many ways. Death by tangled in bed sheets is very correlated with consumption cheese. That's one of the things I talked about before, the spurious correlations that are just coincidence. And you get enough data, those coincidences go away. So the next big thing that I want to talk about is counterfactuals. Wow, is it already 4:59? So counterfactuals is what my research is on, and I think it's just a really fascinating area. And I won't go too much in depth here, but I'll try to give you a flavor of it to give you an appreciation. And I think it's in the next slide or the slide after. Why, when you say thank you to somebody, you may not mean it, or you probably don't mean it. So here's a statement. If I had taken the freeway, I would have gotten home earlier. You know, you took the side roads, you saw the freeway was busy. Maybe, I don't know how many of you are driving yet. Probably not even nowadays. But if you're driving, and maybe you're with your parents, and you see it's busy, you take the side roads. But it took you an hour to get to where you wanted to go, and normally would have taken you 15 minutes. And you think, I should have taken the freeway. I should have just stayed there. So what you're really saying is, but if you had not taken the freeway, this is a counterfactual statement. So the decision has not been made that you take the freeway if you had not taken the freeway, right? And so if you break apart the word counterfactual, it's counter to the facts, which maybe is a little too simplistic. So we'll dive into that a tiny bit. And here's a question. If I take the freeway, I'll get home in less than 1 hour. Is that counterfactual? Anybody? I see some comments here. Couldn't they both be outputs of one cause and have no real causal relationship? Couldn't they both be outputs of one cause? I'm not sure what Neil's referring to, maybe the death by tangled in bed sheets or spurious correlations. So correlation is always where you have one cause affecting two different things, and those two other things seem to be related, and they actually are related, but they seem to be directly causally related. When they aren't, there's not necessarily an arrow between X and Y. Here, well, okay, I'll go back really quick because I think this is valuable and important for our discussion right now. So here's an example of a causal relationship where X causes Y, but you have this third variable, which you may not even know about, that causes both X and Y. Now you take away this arrow from X to Y, then X does not cause Y directly at all. There is no causal relationship between X and Y, but it might seem like that because as X increases, Y increases too. Maybe the famous one somebody mentioned, I think Kai mentioned, the ice cream, right? Ice cream sales and burglaries. They seem to rise at the same time. And the reason is because when it's really cold, nobody wants ice cream and nobody's out burglarizing other houses. So if you increase if the temperature increases, then this Z is maybe temperature. Now, oh, everybody's hot, they're outside, they're enjoying the day, they get more ice cream, and because everybody's outside, now more burglaries happen. But if you shut down the ice cream stores or carts, that's actually not going to have any effect on the burglaries. Eric says, I got mugged while having ice cream. Let me fast forward here. Counterfactuals. All right, so if I take the freeway, I'll get home in less than 1 hour. That is a counterfactual statement. Now, it might turn into a real statement if you actually do decide to take the freeway, but the decision hasn't been made yet. So right now it's counter to the facts. You don't know. And now here's an interesting question. If I take the freeway, I'll get home earlier than not. Now this is always a counterfactual statement, because either you choose to take the freeway and then the statement still involves not taking the freeway and comparing, or you didn't take the freeway and now the statement involves comparing what happened that you didn't take the freeway with what didn't happen that you did take the freeway. So those are two counterfactual statements. I'm going to introduce some notation very, very briefly because we're going to need it shortly. We're going to say X is some decision that you take. In this case, it's taking the freeway or not. So we're going to assign lowercase x to be that we take the freeway, and X prime, this little apostrophe is prime, means that we take side roads. We don't take the freeway. Similarly, Y is the outcome, capital Y, where the lowercase y means that we got home earlier. Y prime means we got home later. When I write P parentheses, that means the probability of whatever's inside the parentheses. So here it's probability that lowercase y, we got home earlier, had we taken the freeway, which is lowercase x. This bar, a vertical bar, means it's conditional on or given. So this is the same probability here that we got home earlier, but that we would get home earlier had we taken the freeway, given that we chose to take the side roads. So this is a pretty interesting question too, or probability, because these are conflicting. We're saying that we actually did take the side roads. Now we want the probability of getting home earlier when we don't take the side roads, when we take the highway. Well, that seems sort of difficult to calculate. How do we calculate that? We can't go back in time. So we can't take the side roads and see what the outcome was, and then go back in time, not take the side roads, go take the freeway. Now we see what the outcome was, and now we'll be able to understand these probabilities better. That's not possible. You can't. No amount of experimentation can tell you that, and that's why these are called counterfactual. So how do we test these counterfactual questions? So we can't go back in time. In order to truly test it, in order to get actual probabilities for many of these counterfactuals, we need additional assumptions, which means we need to say, oh, well, it can never be worse than a Bayes rule. That's not the additional assumption. So Bayes rule works and doesn't need any assumptions whatsoever. Reading that from the chat. These additional assumptions are something like, when we decide to take the freeway, it will always be better. We will always have a shorter time than taking the side roads. Some of these are pretty strong assumptions. The kind of assumptions where if you know this information, you already have a pretty good idea of the answer. Sometimes they're useful, but usually the assumptions necessary are pretty strong, which is not a good thing. We want to only make weak assumptions or no assumptions at all. No assumptions at all is ideal, but that can be very difficult. So I'm going to introduce now a concept of necessary insufficiency. I think this is like the second to last slide or third to last, and then I'll show you something I think is pretty amazing. So I mentioned before, thank you. When you say thank you, is that a counterfactual statement? And it is, because otherwise we wouldn't ask that. Can anybody guess why? Why is thank you a counterfactual statement? Why is that counter to the facts? When you thank somebody, why do you thank somebody? Any guesses? You're telling them to thank themselves. But you're doing the thinking. You know, somebody does something and I say, oh, thank you. And you don't actually mean to thank them most of the time. Kai, you may be right. Let's assume for these purposes that you mean it. You are thanking somebody and you're not just thanking, they didn't just do something. You're like, oh yeah, thank you. You truly have a heartfelt thank you for them. They did something that really deserved your thanks. Let's see, Eric says, because you thank them because they did something for you that you could have done yourself. But that's still nice, right, Eric? If somebody does something and now you don't have to do it because they did it, well, that benefited you. They deserve some thanks. Thank you is nothing compared to the actual thing they did for you, Claire. That may be true. Okay, these are just words. You did something valuable for me, and all I gave you back was words. But let's put that aside. Let's assume this thank you is valuable to the other person. You are basically saying you're better off because they did something than otherwise. Yes, Dennis, that is very, very good. You hit the nail on the head. So the person did or said something and you had a good outcome, right? So we can think of our outcome as y, not y prime. And but had they not did that thing, then you would have had a bad outcome. That's what's happening when you say thank you, right? And you mean it. If somebody does something and it really didn't matter that they did it, like, you would have had the same outcome, the same positive outcome regardless. I don't know. Can anybody think of a good example? I have a good example that I think you'll find funny. Anybody think of a good example that somebody does something and you might say thank you to them anyway, but you don't really mean it. You're just saying it to them because what they did you would have had the same outcome had they not done it. Someone reminds you of something that you already wanted to do. Yeah, I like that one. Jing Kaiyang. That's good. Opening a door. Well, opening a door, that might have been helpful. They passed you the salt and you could have gotten it yourself. True, Claire, but you didn't have to get it yourself. So that's kind of nice. I like somebody reminds you of something that you already wanted to do. That can absolutely happen. And, and the person had good intentions. So the polite thing to do is to say thank you. But it had no effect on your outcome. You were going to do it anyway. And you knew it. You already had your alarm set or whatever. The funny thing that I was going to say, when you say thank you to your teacher after a test, uh, uh, when you were already awake. The fun. So when you thank somebody, what you're really saying is that you believe that the probability of the above statement, that had the person not said or did that thing, you would have had a bad outcome. You believe that probability is high enough. That's when you say thank you. Or you could say thank you anyway, but you don't really mean it. So I just found that pretty interesting. Judea wrote a tweet about this, and it was like a month ago, and so it wasn't me that thought up of this, but he was like, it occurred to me when we say thank you, and I'm like, oh, yeah, thank you is a counterfactual statement, and and so you can think with thank you, oh, but we can never know for sure whether our counterfactual statements are true. So do you ever really mean it when you say thank you? You believe the probability is high or high enough or above some threshold that that you would have had a bad outcome had the person not done their thing, but you don't know. So so maybe maybe you don't really know it when you say thank you. Anyway, say thank you. Be polite. People like it. So here's another example, and I'm getting to the necessity and sufficiency thing, which is, I think, so core to so much in life. Oh, bless you. Sneezing and someone saying bless you. Yeah, well, some right, some people may think, how does saying bless you help me at all? So COVID-19 deniers. Initially, when things first started to explode, and I apologize again if anybody here is today a COVID-19 denier, but I think the evidence is pretty overwhelming that that it is real. But in the beginning, there were certainly a very large number of them calling it a flu. Basically, that's all it is. And they and so is this a counterfactual statement? And what they did was they cherry picked some data in some counties or in some places. It had flu-like stats. It had a 0.1% death rate among the same proportion of people in different age groups and things of that nature. And given enough data and small sample sizes, you will always find things like this. And they said, hey, look, here's the data, it's flu. But even then, they were mistaken. The question should have included, and implicitly it does include, but they hadn't thought of this, had we not taken measures. So, for example, some county in Nebraska, I'm just picking a random state, some small county had a 0.1% death rate. Or or catching it was like a flu-like spread of the disease. But the question isn't, is this a flu-like spread of the disease? It's, is this a flu-like spread of the disease had we not taken the measures that were the extreme measures that we're taking, at least in the beginning of the COVID time, not going to even supermarkets, compared to how we treat daily life with the flu. So here's the thing that I'm excited to show you. This was an article I wrote last year. Which patients are in greater need? And this was in regards to COVID. This happened in March of last year. It's still happening today. Many hospitals have run out of beds. They're turning people away that have other illnesses because of COVID-19. And so COVID-19 doesn't just have the direct death effect, but it has these other effects as well. And so we have this triage need now. Which patients do we accept and which patients do we turn away? We only have a very limited amount of resources, doctors, nurses, beds, and medicine, and all this. It's all being consumed now. Our hospitals, for literally a year almost, have been completely swamped to different degrees. And so this is actually a pretty important question. So who is in greater need of the hospital? And this is a counterfactual question. And this is the article that I wrote on it. And I'll go to it. What did I write? Right. data alone. So this is actually just looking at the data can tell us quite a bit. I'm going to go over to this article and I'm going to show you that we can imagine that we did a test. We did a randomized controlled trial. I mentioned that before, an RCT for men, one for men and one for women. Turns out that in the randomized controlled trial, the experiment we did, and we gave the medicine to men, or we invited the men to come to the hospital, 57% of them survived when they were treated, and 37% of them survived when they were not treated. So that tells us, oh, 20% of men benefit from being at the hospital or getting the medicine or whatever it is that we're triaging. Women, though, 55% of the time, they survived when they were treated, but only 45% of the time when they were not treated. Well, then we subtract that again, 55 minus 45%, that's only 10%. It seems like men benefit more. 57% minus 37% is 20%. Men benefit more from being treated. So should we prefer men to be treated because they're the ones who are going to get the most benefit from the hospital bed or from the medicine that's in limited supply? I probably shouldn't have used men and women because there are other issues with doing that as well, but this is just a toy example. But that doesn't tell us the whole picture, because when we analyze this from a counterfactual perspective, those numbers only tell us a spread, a boundary of at least the lower bound of men that benefit from this medicine is 20%, which is what we assumed, 57% minus 37%, but there is an upper bound of 57%. So it's between 20 and 57%, which is actually it's a pretty wide margin. And women go from 10% to 55%. So it could be that men only benefit 20% extra. What that means by benefit is that if they take the medicine, they survive. However, had they not taken the medicine, they would absolutely die. That's what benefit means. Actually, when you say benefit, anytime you say benefit, that's what you really mean. It's a counterfactual statement. And so this is the probability of necessity and sufficiency. And wow, well, maybe it's only 20% of men who actually benefit from this, from having a hospital bed, but it could be up to 55% of women who benefit. So we should really be only accepting women to this hospital. They benefit so extremely more often than men. So this is a much more complicated question. And in fact, if you have more data, you can answer this question far, far better. You can even get point estimates if you have more and different kinds of data. And this is the counterfactual analysis. This is the kind of thing that I study. And if you want to go to this URL, and I can paste it in the chat for anybody that wants to play with this. This is I'm pasting in the chat right now. This is a little JavaScript app that I made where you can say the probability of benefit or the probability of harm. This is the probability of necessity and sufficiency. It's kind of an odd notation here. You can just think it's the probability that you benefit given had you taken the treatment, and don't worry about this greater than symbol. Think of it as and you don't benefit had you not taken the medicine. This is what this means. So we can look at the lower bounds or we can look at the upper bounds. I have, I think, a fun little animation that happens as you toggle between all of these. This is an impossible area, but you can look at the probability that this is experimentally, you can look this up, the probability that you benefit had you taken the medicine and the probability that you benefit had you not taken the medicine. And then you can run your mouse over the different areas and you can get the probability bounds. All right, so I am just about done here. Basically data alone can tell us quite a bit. Observational data, so this is data that's not experimental. We don't separate people into treatment and control groups. We just observe what happens as they naturally go about things. Did they choose to take the medicine? And then did they actually take the medicine that they bought off their own volition? And if they did that, that tells us a little bit more than if we forced them to take the medicine. And so we combine all this data and we can actually get far more accurate information, counterfactual probabilities, which I think is pretty fascinating. And my research is to narrow those bounds even further so that we can really get to, if we have the causal graph, or at least our understanding of the causal graph of the nature of what we're trying to understand, and we have some probabilities of various nodes in that graph, we can get to understand these counterfactual notions without actually having to go back in time, which of course we can't do. So if we have the observational data, the experimental data, and causal graphs, that can tell us a whole lot. But the problem is, for artificial intelligence, AI, machine learning uses none of this. And so today's machine learning algorithms, they are impressive. They do some impressive things. They exploit patterns in data, and with that, they can make better predictions than many experts in different fields. I'm sure some of you are familiar, in the stock market is pretty much being taken over by machine learning algorithms. Now, you as, I joke around with my family, if you invest in the stock market, you are gambling. You really don't know what you're doing. No matter how much you believe some company is going to do well, you have no idea. If it is going to in fact do well because they're coming out with some new product, or they have some great new managers that have this experience in this other industry that's adjacent to it, or their history shows that they are a very successful manager, or they hired somebody really bad, that's already that was taken into account in the stock price in the sub-millisecond that it happened from these algorithms. So you have no extra knowledge or advantage in investing. It is just a pure gamble if you invest in the stock market. And and if you do well, great. But you didn't do well because of your knowledge or your capabilities. You did well purely from luck. So that might have been different a long time ago, but today it's luck. Machine learning algorithms can generate really interesting things. I'm sure some of you have played with what's the new thing from OpenAI, GPT-3. They're now coming out with GPT-4 in like a couple of years, which is going to be orders of magnitude more impressive than GPT-3, the GOT3 gang. So the deep fakes, I'm sure many of you are familiar with all the really impressive things that can be done with deep fakes, where I've seen a bunch of Barack Obama videos of him saying crazy things, which he didn't say at all, but it completely looks like he did. And it happens in real time using machine learning algorithms. We can now determine diagnoses far better than doctors. We can see these MRIs and these CAT scans and all these imaging technologies. We can see patterns in it that there's no way a human would ever be able to see. And we don't even know why. We don't even know why this thing correlates with cancer. But it is all correlation. So, so machine learning doesn't understand causality. And a classic example here is a machine learning algorithm may notice, you feed it all the data and it notices, oh, the mercury rises in this little tube whenever the temperature gets hotter. And so then the robot, this machine learning robot, it doesn't know whether to, if you want the room to get hotter, it doesn't know whether squeezing that mercury to push it up is going to make the room hotter. It doesn't understand that causal relationship. And so it has no need, no desire to playfully manipulate its environment as we do when we're kids and as adults. And ultimately, AI needs causality to break past where we are right now, which is impressive, but it's all pattern recognition. It's all fitting a function to the data. That's it. It can do some pretty neat things, but it can't reason. It can't understand what the next best course of action is. It can't understand even interventions. It can't understand, it can detect cancer, but it can never tell you what to do about it. And so, so AI will never get out of this rut. Mathematically, fundamentally, it can't. It can't get to human levels without causality. Interventions are foreign, counterfactuals totally just not involved whatsoever. Yeah, some of you may be familiar with reinforcement learning. It sort of deals with interventions, but not really. And I think most of the AI community now is behind causality, but it's a challenge to imbue causality with machine learning. And that's what everybody's working on now, and that absolutely is the future. Causality and curiosity, that's what makes us human. That's what's developed us this far. So ML, machine learning, is beginning to utilize causal inference. We can now transport our machine learning algorithms from one domain to another much more effectively than we were able to in the past because of causality. And we're starting to use that. So that's it for me. And that's where my research is taking me. Any questions? Are the new types of curiosity a decent attempt at causality? A decent attempt at causality. Well, it's one way that researchers are applying causality to machine learning, and I think it is absolutely valuable. So the notion, it's this notion called transportability. You train your machine learning algorithm in one environment. If, for example, you train it to play a particular video game. So, or maybe that's a bad example. You train a machine learning algorithm to detect a particular kind of cancer in a particular kind of scan. You know, maybe it's bone cancer in MRI. I don't know how easy. I'm just making that up. I don't know how easy it is to detect bone cancer from MRIs. But now you have spent a fortune and gotten so much data, and you've trained this amazing machine learning algorithm, and it performs incredibly well. Well, now you want that to be used, and you want all that knowledge of how to understand where the cancer is, where the bone cancer is from an MRI. But now you want it to detect brain cancer in CAT scans. Well, today, without causality, it just can't at all. And or it can, but with very, very poor accuracy, I should say. But if you apply these causal mechanisms in there, it can. And I think that is really, really interesting, because that's what learning's a lot of learning is all about. In educational circles, or in educational academics, cognitive psychology, we call that far transfer skills. Or maybe even near transfer skills. But when you think about it, when you're a kid and you're being taught things, that's how you learn about the world. First you're taught, how to walk, and how to speak, and how to do basic things. And over time, you learn more and more about the world and about how to do things, that you now can be a functioning kid, and then a functioning adolescent, and a functioning adult, and very productive. And so I think that's where some of the excitement around transportability comes from, that we can start to develop these algorithms that just learn more and more, and the learning can be transported from one domain to another. But the transportability there is a bit limited. You can't take an algorithm that has been trained extensively on detecting bone cancer to playing Call of Duty. That won't transport at all. So I think that's an interesting avenue of applying causality, but I think there are some limits there. I think the more interesting areas are causal reinforcement learning, and there's a bunch of areas that a bunch of ways that the researchers are trying to infuse causality with machine learning.
Wonderful. Thank you so much, Mr. Mueller. That was definitely a very enlightening speech. I never really thought too deeply about causality, so that was very stimulating speech that you've given us. And I like that you're able to share a little bit of your research at UCLA. So yeah, we really appreciate you taking the time to talk to us this evening.
Yeah, I had fun talking about it. And I hope that some of you will we'll dive deeper and learn more about causality and machine learning and AI.